Experiment 3, Chromatography. Chromatography is very, very useful and appears quite often in pop culture, where if you're watching any crime show, they may grab some samples or some blood or something and say, run it through the GCMS. The C part of GCMS is chromatograph, because the G part is gas and the MS part is mass spectrometer or mass spectroscopy. So gas chromatography, mass spectroscopy, is a great way to separate and identify components of a mixture. DNA tests also on TV quite often. All those little lines that you see that are matching whether that kid really belongs to that guy are equivalent to chromatography. You take DNA, you chop it up into little pieces, and you run it up a column, and the pieces, people's DNA only gets split into certain size pieces. If you're a pretty close match to, or at least a familial match to, the DNA person. So that's what we're looking at this week, is the chromatography part of both of these techniques that you see on TV. So to talk about chromatography, which is a separatory technique, not an identification technique, unless you have something to match it to. If you have a known compound and you run it right next to your unknown compound, and it's an exact match, then they're highly likely to be the same thing, but not necessarily, just like all the other techniques that we've looked at. It's a single data point, and so you can't bet your life on one data point, or you probably shouldn't. But to talk about chromatography, we have to talk about solubility. And the mantra for solubility is like dissolves like. This is a chapter 3 and 4 topic, so you probably aren't even there yet in class, but we'll do the best that we can. So if you have any questions, make sure that you ask your instructor. So like dissolves like. What I mean by that is that if you have something that has, say, OHs in it, and you have something else that has OHs in it, they'll probably mix with each other very well. But if you have something with an OH and something that doesn't have any OHs, maybe they won't mix so well. If you've talked at all about polarity, molecules that have unequal distributions of electrons across the whole molecule, then you have, or unequal distribution in bonds in various parts of the molecule, then polar molecules mix with polar molecules very well, like water and salt, an ionic compound in a polar molecule. Oil and gasoline would mix really well with each other because they are both non-polar compounds. So the bottom line is compounds that have similar structures or similar characteristics will often mix with each other really well. They are soluble in each other. They don't form two layers. Oil and water don't mix because they're not alike. Oil is not polar and water is polar. So polar and non-polar don't mix with each other. Non-polar mixes with non-polar, and polar mixes with polar. Chromatography was originally designed with separation of separation of colored mixtures in mind, but you can absolutely separate colorless mixtures using chromatography. And for example, gas chromatography, most gases are colorless. The air that you're breathing is a mixture, and you can separate it with gas chromatography. We are going to separate the various colors that are making up a black ink pen, and we're also going to separate the components of a two-component mixture. So you can do it in a variety of different phases. You can have gas chromatography, you can have liquid chromatography, you can even have gas liquid or liquid solid chromatography. In all cases, only interactions are occurring, not reactions. So you're not reacting your compounds together, just like they're not reacting in the mixture. So you are separating your mixture via physical means, as is typical, and your mixture was combined physically. So it kind of makes sense. If you have a chemical reaction occurring, you are not performing a chromatographic technique. You are doing a chemical reaction, and that is something different. So the way that it works is you have a mixture, shown here. Okay, you have a mixture which has a variety of components, and you put it on or in a stationary phase. Stationary with an A, not an E, meaning not moving. Stationary with an E is letter writing materials. So stationary phase is not moving, and you put your mixture onto that stationary phase. And you pass a mobile phase over or through your mixture and your stationary phase. And the components of the mixture will be attracted differently to the mobile phase and the stationary phase. Maybe the component 1 is really strongly attracted to the mobile phase and not to the stationary phase. It's just going to whip right through. And component 4 is really attracted to the stationary phase and not the mobile phase. It's just going to sit there. Maybe you need to change the mobile phase to get component 4 to move. So you are hoping that the components of your mixture are not exactly the same, although they will be similar because they are mixed together. But you're hoping that you can capitalize on the differences between your various components and partition them based on their differing attraction to the mobile phase versus the stationary phase. It's always a competition. Is it more attracted to the mobile than the stationary? Is it more attracted to the stationary than the mobile? And you want to get it through altogether so that you can detect it at the end. Although in thin layer chromatography, you're looking at how far it passes up the stationary phase. It doesn't fly off the end. You don't want it to fly off the end. So if your mobile phase is not polar and your stationary phase is polar, or at least less polar, mobile phase is at least less polar than the stationary phase, non-polar components of the mixture are going to move farther. They're more attracted to the mobile phase than the stationary phase. And if you're doing, say, column chromatography, you do need to get your components to come out at the end because your goal is to separate them and isolate them. And so you might have to change solvents as the experiment goes on, which we do in our experiment, to get the polar component, to get the component, it's polar in this example, but to get the components to move at all so that you can isolate them at the end. So TLC stands for thin layer chromatography. TLC is thin layer chromatography. And it's thin because it is literally thin. I'll show you a picture, but you're looking at a glass plate with some sort of adsorbent material on it, silica gel or alumina. And so it is relatively thin. The mobile phase can be a single component liquid or multiple components making a mixture of liquids. And you're choosing your mobile phase to hopefully get perfectly good separation between your components. And therefore, it's both a little bit of art and a little bit of science. Tailoring your mixture, perhaps, to get good separation of your components can be a real challenge. We give you the mobile phase already mixed for you, so you don't have to worry about that art and science, and just see how well you can separate your components of an ink pen. This is for small scale separations on the orders of milligrams, and not for large scale separations. It's a nice way to see if a reaction is occurring. You run a TLC of your starting material and see where that ends up, and then you take samples out of your reaction mixture as the reaction goes on and see, oh, my reactant dot is disappearing, and I'm getting new dots for my products. And you watch them appear, and you wait until hopefully all of your reactant has disappeared, and then you know your reaction is complete. So your thin layer plate looks something like this. Okay, this white powder is stuck to the plate. Back in the old days, they'd give you a big sheet of glass and a bucket of white powder, and you had to cut the glass and then make a slurry of the powder and dip the glass in there and hope that it ended up nice and thin. Now we just give you a piece of plastic with this white powder stuck to it, and it's already cut for you. It's nice and easy. You put your sample, you spot your sample near the bottom, not all the way at the bottom, for reasons that we'll discuss on the next slide. But it would just dissolve into the mobile phase rather than get carried up the plate. And as the mobile phase, which this will be resting in a little vat of mobile phase, so below this line that you've drawn on there, that's as far up as the mobile phase could come in the vat. And as the mobile phase goes past your dot, it starts to pull the components up the plate. And the components that are really attracted to the stationary phase, to the white powder, don't move up very far. And so you hopefully end up with a dot and some space, and a dot and some space, and a dot and some space, dot, space, dot, etc. And then you draw a line where the solvent stops moving, where the mobile phase stops moving. So according to the instructions in our lab manual, ds is the distance that the solvent travels from the start line. D1, D2, D3, D4 are distances that these centers of these spots traveled, again, from the start line. You'd take a ratio of the two, how far your spot goes versus how far your solvent goes, and that is known as the retention factor or retardation factor, RF. Capital R with a subscript lowercase f. Just a quick note that there are no standard values of RF. You can run your unknown and run a known right next to it and see if they happen to have exactly the same RF. That's, again, a data point that they are likely to be the same thing. Certainly, if they had different RFs, they would not be the same thing. But you can't absolutely confirm it, and nor could you go to a book and say, oh, the RF of this component is, this high. That would not be the case. It depends on the solvent, it depends on the stationary phase, it depends on a variety of factors. In column chromatography, as opposed to thin layer chromatography, you have a liquid mobile phase and a solid stationary phase, and it is placed into a vertical tube. Gas chromatography is technically also a column technique, but the stationary phase is held in usually a coiled up column because it can be so long, up to 30 meters long is the standard length. And so you can't have your instrument 30 meters long. That would be excessive. The stationary phase is just like the powder that's stuck to your plate in TLC, is silica or alumina. And we put it in a vertical glass tube that could be really small, a couple millimeters across, or could be a few meters across. You can do bulk separations from grams to kilograms. If you've ever wondered where the drugs in your pills come from, big vats of drugs being made at a time and purified so that you don't get poisoned with random chemicals, purified using column chromatography for the most part. The mobile phase can be a single liquid or multiple liquids, mixture of liquids to adjust your polarity of your mobile phase. And again, choosing that mobile phase can be complicated. So in TLC, you have this chamber for your mobile phase. It can't be very deep. If it goes above the line that you've drawn on your TLC plate, your dot will wash down into the vat rather than have the solvent move up the plate and separate it into its various components. In column chromatography, this is the column here, just a couple of millimeters across. We're just using a standard glass Pasteur pipette to put our stationary phase in. Sometimes the solvent doesn't drip through here very quick, and so you can take a pipette and you cut the tip of it off, and you use that to blow the air through here. There are specialized columns and specialized pieces of glassware for blowing air through a column chromatograph technique known as flash chromatography. So I want you to think about, can you predict ahead of time how many spots you're going to see for the ink pen in TLC? Do you know how many components make up a black ink pen? Think about the difference, something to discuss in your lab report if you're writing a lab report for this lab, the difference between something being absorbed and adsorbed. Absorbed is like into a sponge, filling up pores. Adsorb is a physical interaction between like components often. When you're doing column chromatography, your components, there are only two of them. So how many colors, how many bands of sample are you expecting to see come out the bottom of that column? And what would happen if instead of doing water first, you did ethanol first? What would happen if you did ethanol first instead of water first? How is that going to change your TLC? That's our brief overview of chromatography. I hope you enjoy the lab.